Artificial intelligence works in a world full of uncertainty. The data it gets is often incomplete, noisy, and even contradictory. But still, AI is expected to make smart and trustworthy decisions, predictions, and recommendations. This is why probability and statistics are so important. They give AI tools to deal with uncertainty and form the backbone of decision making. Ever wondered how AI predicts the future or even creates new content? The secret lies in probability. AI doesn't give guarantees, it works with chances. For example, a model might say there is a 78 chance a customer will leave. In reinforcement learning, probability helps AI balance between exploring new options and sticking with proven ones. And in generative AI, probability decide what word, pixel, or sound come next, powering everything from chatbots to image generators. That is why probability matters in AI. It is the engine that helps machine handle uncertainty and still make smart, reliable decisions. Let us break down some core probability concepts in simple terms. First, a random variable. This just means an uncertain outcome, like rolling a dice and getting a number between 1 and 6. Next, the probability distribution. It assigns chances to each possible outcome, helping us know what is more or less likely. Then we have expectation or mean. This is simply the average outcome if you repeat an event many times. Finally, variance and standard deviation. This measures how spread out or uncertain the outcomes are. Together, these ideas form the foundation of probability, and they are the tool AI uses to make sense of uncertainty in the real world. Bayes theorem is a way to update our beliefs when you see new evidence. Think of it like this. We start with a prior belief called a PH, then we ask, if my belief were true, how likely is the evidence? That is the likelihood, P E bar H. We also consider the overall chance of evidence itself, that is PE. Finally, by combining all of these, we get the posterior PH by E, our updated belief after seeing the evidence. In short, prior belief, evidence, and then updated belief. This is how spam filters, medical tests, and even AI system keep learning and improving. Let us see how Bayes theorem works with a spam filtering example. First, we start with our prior knowledge. 20% of emails are spam, and in those, 60% contain the word lottery. But in genuine emails, only about 1% contain lottery. Next, we get new evidence. An email arrives with the word lottery. When we calculate, the total probability of seeing this word is 0.128. Finally, we update our belief using Bayes theorem. The chance that email is spam jumps to about 93.75%. This is the power of Bayes theorem. It helps spam filters, medical tests, and even AI system make smarter decisions based on the evidence. Bayes theorem is not just theory, it powers many real-world applications. First, naive Bayes is widely used in text classification, like detecting spam or analyzing sentiment in reviews. Next, Bayesian networks help us model complex cause and effect relationships, useful in medicine, troubleshooting, and decision making. And finally, Bayesian optimization is a powerful tool for tuning machine learning models, making them smarter and more accurate. So, bias is everywhere, from emails to AI, shaping smarter systems around us. Distributions are the shapes of data. They help us understand how information is spread out, and this is a key part of AI and machine learning. By looking at data distributions, we can model uncertainty, make better predictions, and find real insight in complex datasets. From simple yes or no decisions all the way to advanced neural network outputs, distributions guide how we read, understand, and use data. Let us look at discrete distributions, which are all about counting events. First, the Bernoulli distribution. This models a single yes or no try, like whether someone clicks on ad or not. Next, the binomial distribution. This extends Bernoulli to many trails. For example, out of 10 people visiting a website, how many actually make a purchase. Finally, the Poisson distribution. This helps us model rare events over time or space, like the number of website crashes in a week or how many customer calls arrive each hour. Together, these distributions give us powerful tools to understand and predict real-world events in AI and machine learning. Let us talk about continuous distribution, the model that helps us understand real-world data. First, we have the normal distribution, also called bell curve. It is everywhere in nature, measurements, and even AI. Defined by mean and standard deviation, it is backbone for regression, PCA, and noise modeling. Next, the exponential distribution. This one models waiting times, like when next customer arrives or when a system fails. Because of its memoryless property, it is perfect for survival analysis and queuing theory. And finally, the uniform distribution. Here, every value in a range has equal probability. It is simple but powerful. It is widely used for random sampling and initializing weights in neural networks. Together, these distributions power statistical modeling, helping AI and data science make sense of continuous and real-world values. How do distribution power artificial intelligence? Let us break it down. First, Gaussian distribution. They drive regression models, PCA, and even noise modeling. Thanks to the central limit theorem, they are everywhere in AI. Next, Poisson distribution, perfect for anomaly detection. In cybersecurity and fraud detection, they spot unusual spikes or sudden drops in activity. Then comes softmax, a hero in neural networks. It converts raw output into probabilities, helping AI classify and measure uncertainty. And finally, generative models from GANs to VAS. They learn entire data distributions to create brand new, realistic samples like images, voices, or text. That is how distribution meet machine learning, turning raw math into real-world AI power. In AI, not every improvement is real. Sometimes it is just random noise. That is where hypothesis testing comes in. It helps us separate genuine progress from false signals, giving us confidence that our models truly work. As Edward Deming once said, in God we trust, all others must be data. And in AI, data-driven decisions are everything. Let us make hypothesis testing super simple. It is just 5 steps. Step 1. Start with null hypothesis. Assume nothing is happening, no effect exists. Step 2. Define the alternative hypothesis. This is the effect you are hoping to prove. Step 3. Choose your test, like a t-test or ANOVA, depending on your data. Step 4. Compute p-value. This tells you how likely your results are if nothing was really going on. And step 5. Make your decision. If the p-value is small enough, you reject the null and say, yes, the effect is real. That's it. 5 simple steps to turn data into confident decisions. Here is how A/B testing works in real AI products. Step 1. Set up hypothesis. The null says old and new algorithms perform the same, while the alternative says the new one improves click-through rates. Step 2. Run the experiment. Show different users, different algorithms, and collect click data over time. Step 3. Analyze results. If the p-value is small, like here 0.03, it means the improvement is statistically significant. Step 4. Deploy the decision. With confidence, roll out the new algorithm to everyone because the gain is real, not random chance. That is A/B testing, turning data into smarter AI decisions. Hypothesis testing is not just theory, it powers real AI applications. First, model validation. It checks if your new model truly beats the baseline, so you don't deploy something that only looks better by chance. Second, feature important testing. It tells us which feature genuinely impact performance and which ones are just noise. This is the key for feature selection and making models interpretable. And third, A/B product experiments. From recommendation systems to AI changes, A/B testing ensures that improvements are real and statistically significant before a full rollout. This is how hypothesis testing keeps AI reliable, trustworthy, and effective in real world. Three powerful ideas drive modern AI. First, Bayes theorem. It updates beliefs with new evidence, powering probabilistic reasoning and machine learning. Second, distributions. They capture uncertainty in data, helping us model and predict real-world behavior. And third, hypothesis testing. It separates true effects from random noise, giving us confidence in our decisions. And these are not just abstract math, they are behind fraud detection, medical diagnosis, recommendation systems, and even the predictive text you use every day.